Welcome back. In the previous video, we covered regularized method for regression, where we start to use ridge, lasso, as well as elastic net to impose penalty to enforce our coefficient so that it doesn't actually explode or get a large coefficient. In this video, we're going to cover polynomial regression. One common pattern with machine learning is to use linear models trained on non-linear functions of the data. This approach maintains the generally fast performance of linear methods while allowing them to fit a much wider range of data. Now, this description is directly from scikit-learn. I just want to actually highlight this so that you can actually understand the intuition before we go into the actual modeling and the code itself. Now, take for example, a simple linear regression can be extended by constructing polynomial features. So this is the key word here, polynomial features from the coefficient. In the standard linear regression case, you might have a model that looks like this for two-dimensional data. So basically what you have is that y is equal to a constant. Okay, so it could be beta 0, just using a slightly different notation, beta equal to 0, and then you have beta 1, x1, and then you have beta 2, and x2. So that's your standard linear regression. Okay, so if you take a slightly different approach, if you want to fit a paraboloid, to the data instead of a plane, we can combine the feature in the second order polynomial so that the model looks like this. So you have the standard, you have this is the intercept term, this is the first independent term, second independent, third, fourth and fifth. Now the interesting part is this is x1 multiplied by x2, and this is x1 square, and this is x2 square. So in this case now we have 5 independent variable plus a constant term, which is the actual intercept itself. What happened now is that we conduct or perform a transformation. Okay, how does the transformation goes? Basically, you are creating a new variable called z. Okay, what is z? Okay, let me just use a slightly different color. Let's use green here. So you have x1, which is the original, x2, original, x1 times x2, x1 as well as x2. So what was the transformation that was really being done in the end? W0 is still the same. You have now z1. Okay, which is your z here, and then you have your z2, z3, z4, z5. Now suddenly they all look completely linear. Okay, in essence, these are actually the transform variable of this original data. Basically, this has been relabeled so that our problem is now looks like this, and basically it looks, guess what? It looks linear. Although, in essence, when you really look at it, is actually quadratic and the underlying. Now we see that the resulting polynomial regression is the same case as the linear model we've considered above. The model is linear with respect to W and can be solved by the same techniques as per normal linear regression. By considering linear fits with a higher dimensional space built with these basis functions, the model has the flexibility to fit a much broader range of data. So this is really the basic ideas here that is being utilized and incorporated into the scikit-learn library. So let me just relabel this so that it's actually clearer. So let me just stop this. Don't want to save the graphics. I've provided the link to the scikit-learn so that you can actually refer to that. So basically extending the linear model with basis function. Okay, let's look at these codes here. So we've imported the standard library. So we're going to generate some random numbers. So let me just show you what it looks like. So notice the parabolic effect here. Okay, so it's actually, it curves upward. So the actual equation is y is equal to x cubed plus 100. The 100 really is, we're generating our random number at 0 because it's random normal and 100 of them. And we multiply by 100, so it will be 0 plus or minus 100, but we shifted it upward by 100 by doing this. Okay, so this is really the scatter diagram. We're going to have a look at linear regression to see how well it fit. Okay, so import the standard libraries. Again, instantiate, and the next line is really fit, and then the third line is really conducting the actual in-sample prediction to see how well the linear regression model actually explain the variable or variability. Okay, so again, these are the typical plotting. We have a scatter diagram of the original data set, and we're plotting the actual model prediction. And finally, we have a score of the R2 or the R square to see how well linear regression explained the data, observed data. Okay, so you can see here is 76%, all right, and which is on the low side, and you can see that the linear regression just don't really have a chance of fitting this model, or rather the underlying data, well, because it just doesn't have the ability to curve here. All right, so let's look at the polynomial. Okay, so the process is slightly different from linear regression. You have a pre-processing library that you import the polynomial features, which is the features that we talked about here. This is the feature extraction that we're looking to do here, or polynomial features. We're transforming it. So the next thing is, again, the standard process of instantiating with 2 degrees and fitting or fit transform the original x to give us the x polynomial. Now we're instantiating the actual linear regression as per before. So notice that we've transformed our data from this x to z. All right, so we've relabeled it. Okay, basically it's in this form now, whereby the original was this form. Right, so now we are just going through fitting our linear regression, okay, using the transformed data. So instantiating, fitting, and finally predict. So let's plot this and let's see how it works. So this is the observed, the dots are the observed data, and notice that the transformed data or the polynomial can actually follow the so-called distribution or explain the distribution or the underlying so-called properties much better. The R squares is substantially higher at 91% when you compare to the linear regression of only 76%. So having developed that intuition, we're going to dig into actual data now, the Boston housing data set that we've seen before. So we're going to download the data, import it into our library, df Boston or df Boston here, rename the columns, and we're just going to look at DIS as well as Knox here. Now I've hidden this, so I'm going to leave that with you to actually run that exercise. I'm just going to CORR run the correlation or df Boston, and just for you to actually visualize this in terms of the 2 variables looking at is DIS as well as NOx, which is this one here. It looks really negative, and what you can't see here is actually the so-called characteristics of it. So that's why we're going to plot that up. We're going to store the DIS into the X and NOx into the Y underscore Boston. So let's plot that out, and you can see that this is a little bit different from what we observed before. Nevertheless, it's not linear. Clearly, it's not linear. It seems to actually go down this way. So again, we're going to run the linear regression model, and the lines of codes are the same, so I won't walk through the line by line. And as you can see, the linear regression does really poorly. The R square is actually only 0.5, so it really should be that. And if we now try quadratic, quadratic meaning x squared, so this is the degree is equal to 2, and again we do the fit transform and instantiate our linear regression, fit our model, and this x fit here is basically we are taking the lowest and the highest point rather than fitting, this is X fit is for our prediction rather than the whole idea here is that we're gonna basically rearrange the so-called X fit. All right. So let me just show you what it looks like. X fit. Okay, so this is what it looks like. It's on a step of 1. Okay, and so let's just conduct our transform and transform in the internal part and also run the actual prediction itself. And now let's plot that out and have a look what it looks like. Okay, so when it comes to the actual prediction itself, what we have done is that we take one step by one, instead of trying to make a prediction on every single dots here. Okay, so we are fitting it within this so-called space here. And what you can see here is that the R score has improved, okay, to 0.7 from 0.59, which is quite a substantial improvement. Now, unlike what we did before, which is the generated data, we know what the model is actually x to the power 3. What we could have done is to actually, instead of 2 here, we change it to 3. It would have fit this substantially better. So just to prove that point, I'm going to give it to you as an exercise a bit later. But coming back here to the Boston data, we can't tell to what degree this is supposed to be. Okay, so the only way for us to do is just keep trying different parameters and see how it works out. So now we're changing the polynomial features to the degree of 3 and run the lines again, and this time, and you can see that it probably start to overfit the data. Notice they actually start to curve downward. The R squared didn't really improve that much. It's 71% compared to before 70%. Yes, it has increased slightly, but it doesn't seem to actually have improved the R square all that much. Instead, we might seem to have a case of overfitting. Now we've come to the end of the video lesson. This is still not a completely satisfactory model, but nevertheless, the purpose of this exercise video is really to illustrate to you the whole idea of linear regression, but in a polynomial sense. And the idea of extending your linear models with basis functions, transforming the original x to z with relabeling of data and also a transform feature. So that's the basic idea of the polynomial regression. And now what I'd like you to do is you make use of the Boston data set and try higher feature. Okay, 2 exercises I want you to do. One is increase the actual degree to maybe 4, all right, to see what it looks like. And the second thing I'd like you to try is coming back to the generated data that we have, because this is x to the power of 3. What happens if you change the so-called polynomial degree equals to 3, and how would this R square change? Would it improve or would it get worse? So with that, I'd like you to pause the video, try that out. When you come back, I will wrap up the lesson. I really hope that you've tried out the exercise and gained a little bit of better insight and also a better intuition and feel of modeling using polynomial regression. With that, I will end this video. Just to let you know what's coming up is that we're gonna step into a slightly different realm of dealing with non-linear relationship. Instead of using polynomial regression, we're gonna start venturing into ensemble models. So with that, I'm gonna leave you and see you in the next video.